I'm just hoping that we can leave that part in where only Sam is able to push the record button. All right, right, welcome to day 3. Hope everyone's feeling as good as they were on day 1. Today, let's see, we're gonna get started talking about some of the core functionality in Rosetta, or some of the, in this lecture we're gonna cover the utility library, the numeric library, and then a large section of core in not all that much detail. But at least want to give you a sense of the highlights of how these libraries are constructed. Okay, so in utility, utilities library has a whole bunch of useful data structures and some very generic code that's useful in a lot of different scenarios. I'm going to talk about utility vector 1. I mentioned utility vector 0, this fixed size array class, IZ stream, which is pretty useful, and then utility tag, which you had a little bit of experience with in evening lab number 1. You might also find useful, but we're not going to talk about utility heap, which is a heap data structure, or this lexicographical iterator. In the numeric library, I'm going to cover XYZ vector and XYZ matrix, homogeneous transform, which is a convenient way of representing linear transforms, rotations and translations. Some of these common numeric functions, such as computing the cosine of an angle given 3 points, or the dihedral of an angle given 4 points. And then I think I'm not actually going to cover numeric interpolation. There's some other very useful pieces of code in numeric. In the numeric deriv directory is generic logic for computing the F1 and F2 derivative vectors for functions of distances, angles, and dihedrals. So if you have a new potential function and you need to compute the derivative with respect to an angle or a dihedral, then you'll want to look at the code in this directory instead of implementing it yourself. The math is actually very tricky. And then there's some code if you want to take a string and convert that into a mathematical expression that can be evaluated. There's a scanner, and there's code to convert that into an abstract syntax tree, and convert the abstract syntax tree into expressions. And so that's fairly generic and probably useful in a number of different scenarios, but I won't be talking about it today. In Core 1, I've already spent a fair amount of time talking about graph. Also in Core 1 is this types.hh, which is where the size and real type defs are defined. In Core 2, we have the ID directory, which has atom ID, DOF ID, and torsion ID, which are just indices into other data structures for atoms, DOFs, and torsions. I'm not going to talk about core kinematics, which is also part of Core 2, but that will be covered in greater detail this afternoon. There's also the chemical directory, which has two useful, or some highlights out of it include residue type and residue type set. Residue type has a special relationship with class residue in core conformation, and I'll talk about that in some amount of detail. Conformation has residue, as I just mentioned. It also has conformation, which you interacted with just a little bit yesterday, which describes sort of the whole Euclidean and internal degrees of freedom of a system. There's also conformation symmetry, which has some information about how you would represent symmetric structures in Rosetta, and I'm going to give you just a little bit of a description of how that works. And in Core 3, I'm going to talk about Pose and ScoreFunction. Class energies you interacted with just a little bit already, I believe. The energy graph lives in class energies, and I'll talk about the energy graph a little bit more. And then there's this long-range energy container, which is also contained, or sort of set of these are contained in the energies object. And in particular, these things relate to the energy method hierarchy, which I'll talk about in a little bit of detail. You might also find some of these classes to be useful or interesting. So let's get started with utility. Okay, so this is at the very top of the library hierarchy. So it's got very generic stuff, and lots of things depend on utility. So the first one is utility vector 1. It's templated on the class that you're going to try to put into the vector. So you could template it on integer, or size, or real, or pose. You can put anything you want in utility vector 1. It has this nice property that it indexes from 1, which is what all of Rosetta uses. So if you weren't yet aware, Rosetta has this history of coming from Fortran, where in Fortran everything indexes from 1. So you start in your array, say, from 1 to n. And so that's what I mean by index from 1. When we moved from a Fortran representation of the code to C++, that index from 1 behavior stuck. So we still index from 1, and so it's nice to have a data structure that indexes from 1 as well. This is sort of different from standard vector, which indexes from 0. And so if you try to replace a vector 1 with, or a standard vector with a vector 1, you'll have to change your logic so that you don't run off the end of the vector, or start reading from the 0 position, rather. What's really nice about utility vector 1 is that it asserts boundary conditions in its operator square bracket. So when you're trying to access an element out of the utility vector, it'll make sure that the index that you've given it is actually valid for the vector. So standard vector, in contrast, doesn't assert boundary conditions in its bracket operator. It has a separate method for which it'll actually assert that, which is this at method. But no one, I don't think, has ever used the at method in a standard vector, and no one in Rosetta uses it either. So that's basically the most worthless thing that you could have added. But what's really nice about the assertions that we have for the operator bracket is that they're removed in the release build. So we're not spending time in production runs asserting boundary conditions. The way that utility vector works is that it's actually derived directly, or it's indirectly, from standard vector. So it shouldn't come as all that much of a surprise that it works with all the standard STL algorithms like sort. So you can sort through using a utility vector. If you are interested in say converting from a standard vector that someone has left in the code to something that actually asserts the boundary conditions in the operator bracket method, then you can use a vector 0. So utility vector 0 and standard vector are perfectly interchangeable, but with the big difference being that you actually, if you run in debug mode and you don't index out of bounds, then your code is probably working correct. Okay, so another fun class is this fixed size array, which is templated on two things. It's templated on the size of the thing that you want, and then the type that you're going to contain. So the size could be 4, and then the type could be real. Yeah?
What do you mean by templated? Like, it's inherited, or?
That's a big question. So templates are, they're almost like a find and replace mechanism for the compiler. So you say real for T, and it says, okay, everywhere that I see the letter T, I'm going to put real. And so if you had this as templated on 4 and T, then it says, okay, I'll make this a real array of size 4. And it's actually really find and replace. Like it's not terribly sophisticated in terms of how the mechanics work underneath the hood.
You don't even have to make substitutions at compile time. It makes substitutions.
So you write this code. It makes the substitutions at compile time. So you write the code once, right? And then if you want an array of size 4 of ints and an array of size 4 of reals, you don't have to write the code twice. You just say, yeah. When you declare it, you say, this is my utility vector 1 of real, and I know it's going to work because all the utility vector 1 code has worked before with all these other types. Right? So the type isn't the important part of the functionality of the class in most cases. And so lots of container classes are templated in this way. But yeah, that templates didn't really make it into the set of topics that we're going to cover in this course, but we use them all the time, and they're kind of useful to know about. So, sorry about that. Okay, so the fixed size array will make a small array. Well, it'll make an array of exactly the size S that you give it. And so, if you want to allocate a little array and you want to do so very quickly, then this has the advantage of declaring that array on the stack. And talked about earlier how new and delete are quite a bit slower than just allocating a variable in the stack. And so this saves a lot of time if you've got tight loops where you don't want to spend a lot of time in new and delete. So this is where that class is useful. Okay. We have this IZ stream class, which is pretty sweet. It's a wrapper around two things, and then it dispatches to one of those two things. The first thing that is a standard F stream, or IF stream or something. So you can open a regular file with this. The other thing that it wraps is a gzipped file. And so if you try to open a file and it's not there, it will automatically look for the .gz form of that file. So it'll take the name and append .gz. It'll try to open that, and it'll try to open it as a zipped file. And then if it finds it, then it'll just read from that just the way it would from a standard file. So it'll decrypt it as it's going, or unzip it. Yeah, so if you use this, then it's really easy to compact the amount of space that your input files are taking on the cluster. So I recommend just having this as like an, if you need to open a file, this is how you should open the file, so that in the future you can zip that file and it will still open just fine. And you won't have to change any of your code. So utility tag is the class that we use for representing the contents of an XML file. In Rosetta scripts, we have this ability of specifying a protocol from a text file, and we encode that protocol as like pieces of data in this recursive data structure called a tag. So the thing about a tag is that it holds owning pointers to itself, which are its subtags. So in Rosetta scripts, you would have a tag, for instance, for say the report to DB mover, right? And so this is one tag, and some of the subtags of this guy are this thing. So the feature subtag would be a subtag of this report to DB mover, and it is itself a tag. So it has a name property, for instance, in the same way that the report to DB mover has a name property. So each tag has a name. Each tag has a set of options. So this is a little confusing. Name is actually report to DB in this case, and then options includes name, so such as report scores, which is something that you use to name the instance of your mover for your Rosetta scripts. Sweet. This again. So it's the option set is a map from string, such as name, to the other thing that it's containing, which is string. And in this case, the name would be, or the first thing would be name, and the second would be setup sim. In the second case, it would be resource description as the first item, and then simdef as the second item.
So the tag is simdef, or where are the tags?
So the tag represents, so one tag object would represent this block here. Okay. And it has some properties for itself, and then it also has children subtags, so which would be these two: feature name equals score type features, and feature name equals structure score features with the ScoreFunction option. And so, so when you pass in a tag to, or when you want to define a new mover, you can have it take subtags, so you can pass arbitrarily complicated data to your mover through the XML file. Okay, so that concludes utility. The next library is Numeric. It's slightly less general than utility, and it depends on some of the code in Numeric. So it has different functions that, for instance, take arguments of the form of utility vector 1s, but it defines plenty of useful classes on its own as well. All right, so XYZ vector is templated on type T, and we usually use XYZ vector of type double. So there's a useful type def that lives in core. The type defs numeric XYZ vector of double to vector. So if you're in core, you can just use this, note the capital V here. And then, so double would then get replaced here in double X, double Y, and double Z, giving you 3 coordinates for an XYZ point in space, or a vector in space. So there are a lot of useful vector operations. I invite you just to look at what's provided in this class by reading through it. There's like a dot product and a cross product. You can normalize a vector to unit length, taking care of the boundary condition where, or I'm sorry, the edge case where you have a vector of length 0. You don't want to divide by 0 when you're trying to normalize a vector. And it's nice to have error handling sort of built into this class. Yeah?
So that class works for XYZ vector only, or it does, sorry, for XYZ matrix, or it can work for any multidimensional vector?
This works for a vector in 3 space, and it has 3 doubles. So it's a vector as opposed to a matrix. So you can't represent a matrix with this class. I mean, you get literally 3 doubles if you use double here. If you use float here, you get literally 3 floats.
With that class, you can make also operations with matrix, right?
There's another class, XYZ matrix, that's also templated on type T. So you can have this templated as double. And then that would give you 9 variables, all of type double.
Okay, what if you have a vector with 4?
Then that's not provided here. Yeah. So this is specifically for operations on vectors of size 3 or matrices of size 3, which are really useful for operating in Euclidean geometries. But if you're in some sort of back to the future sense where you've got like time as your 4th dimension, then that won't work for you.
So for your XYZ vector from the previous slide, why do you define it as 3 separate variables and not like an array of size 3?
Let's see. So it's sometimes useful to just, I mean, if you're writing the code to know X, Y, and Z, I think it would be possible to have it as an array. It's more or less treatable as an array because they're going to be right next to each other. So you could take a pointer to X and then ask for that pointer with the bracket operator 2, and that would give you Z. That would be a little wild, but you could do it.
So that still guarantees that the memory of each variable will be right next to each other?
Yeah.
Okay.
As you declare a class, like it's going to group memory in space when it's allocated, and then the order in which pieces of memory are declared determines where they appear in that class. So XYZ matrix is useful for representing rotation matrices, though I personally recommend using homogeneous transforms, which are this combination of rotations and translations into a single class. So instead of having one matrix for, one object for your rotation and then a separate object for your translation, you put them in the same object. And then this is basically a 4x4 matrix, except the bottom row of this matrix is 0, 0, 0, 1. So you don't actually need to allocate this bottom row. But then you can treat it just like a 4x4 matrix. And so the operations on a homogeneous transform have all properties that a matrix would give you. So you can invert a homogeneous transform. You can right multiply. You can left multiply. Multiplication of your matrices is associative. So what is this like? So if you have this sort of representation, then the column here, x, 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 y, x, z, defines a sort of x vector. Like think of this as your x-axis. Yx, yy, yz gives you the y vector. Zx, zy, zz gives you your z vector. And then this point P is the location in 3 space where this little coordinate frame lives. right? So it's homogeneous in the sense that you treat coordinates and vectors in the same representation. So typically often what you want to do when working with homogeneous transforms is you've got this frame F and this point Q prime, and you want to know where Q is inside this frame. But you have this thing, so if you have a local coordinate and you multiply it by homogeneous transform F, then that will give you the global coordinate for that point. So if you have the global coordinate, what is the local coordinate? And the answer is that, I think this wrapped. No, that's the slide number. Okay, so down here at the very, very bottom of the screen, you can walk through the logic to go back to Q from, no, it must have wrapped. I think the equation is on the next line. Let me see if I can just exit out here so you can see it. Well, it's now tiny, but so the equation here is that delete a line. All right. That's unfortunate. Okay, so so you can multiply both sides of this equation by the inverse of F. So if you invert this matrix and multiply on both sides, then you get the identity matrix here, and then F inverse times Q prime. And then that will give you Q. And so you can just ask the homogeneous transform. It has like a dot inverse method. And so you can just ask it for the inverse matrix, and then multiply that matrix by a coordinate. Yeah.
So what would the advantages of like this be over like quaternions or something? Because I mean I know quaternions don't do spatial transformations, but with quaternions you can do rotations in like much fewer operations than a rotation matrix. It's like
that's not true.
Yeah.
You always convert to a rotation matrix when you're actually going to.
No, definitely not.
I mean, you can do a series of quaternion multiplications.
I can show you after. You don't need to generate a rotation matrix.
How do you take so if you multiply quaternion by a point?
Yeah, but it's like a series. It's that you don't just multiply it. There's actually a algorithm that they use in like to do like 3D graphics that is much faster. It's 16 operations compared to 40 operations. I can show you after.
Okay. Yeah. I should look at it more closely. The reason I haven't used quaternions in the past is that we're not in a danger zone where we accumulate, say, numerical drift from our rotation matrices.
Mm-hmm.
But I think
from a speed aspect, it's much faster.
Okay.
That's why I was interested in that.
There's a quaternion class in Numeric.
There is a quaternion class in Numeric.
Compare and look at some of how the rotation operators are overloaded and implemented and all that sort of thing. See if maybe someone else has already added some of the things that you're thinking of. And if not, hooray, bring your own project time.
Yeah, there are quaternion rotation already.
Okay. And so does it handle translation simultaneously with rotation?
In a single quaternion, there is a rotation and translation at the same time.
What? No.
Yeah.
Rotation just describes, quaternion just describes a rotation.
No,
not
the
translation.
quaternion describes the position. The
It
rotation
gives you a
vector
vector
regarding to the
No.
that you can
central
rotate about.
No, it's just a rotation about this entire method. It's no positional information.
Right. So this gives you
Yeah.
translation.
Yeah. This is purely from a speed aspect. Yeah.
Well, then you still have this this first operation of translating
Right.
to the origin and then to
that-
translate back. Well, so let me show you
Okay.
what associativity gives you. Did I kill this slide? Okay, so right, so matrices and matrix multiplication are the representation for everything. So matrices are invertible and associative. Imagine you're performing a string of rigid body transformations on chain B. Let's say you've got chain A and chain B, and then you're going to rotate about some axis V by a certain amount. Then you're going to translate along this new axis V prime by 3/10 of an angstrom, and rotate along this final axis V double prime by a final amount. So then in homogeneous transforms, this happens as these three operations. So rotation matrix about V, translation about V prime, and a final rotation about V double prime. And then you compute that, for point P, I, for all I, right? In all the coordinates in chain B, right? So because of associativity, you can compute this single transformation, which is the multiplication of a rotation, a translation, another rotation, and have that compactly represented as a single transformation. And then you can get away with just computing this one matrix point multiplication for all of your points. And I'm not entirely certain, but I don't believe if you haven't represented translations as part of this that you could do that with quaternions.
No, you definitely can't. But I still think this is more operations than doing it the other way. But we can discuss that after.
It can't be.
Sure it can.
No, I mean, you only have one matrix vector multiply for 3 operations that you're going to apply to every.
Multiply is a lot of operations of this. I mean, I'm considering an operation of addition or a multiplication.
Mm-hmm.
Yeah, matrix multiplication has more.
Okay, so I haven't counted,
Okay.
but
Well, there you go.
you add up enough of these. You add up enough of these, and you have one matrix multiply for your entire set, versus 16 plus 16 plus 16 plus 16 plus 16. However many of these kind of movements you would have.
If you do a series of translations and rotations, then yeah, I agree. This is probably faster at some point. But I'm just saying for one rotation or a series of rotations and one translation, the quaternion has fewer operations.
Okay.
That's all I'm saying.
Cool.
Yeah.
I'd like to learn more about that. Okay, so if you'd like to see an example of how homogeneous transforms can be used, you can take a look at protocols match. Or if you're interested in quaternions, they're also in Numeric. XYZ function.hh, or XYZ functions.hh has a lot of useful functions. So you can multiply a matrix and a vector by the transpose. You can compute the angle and radians of 3 points. You can ask for the dihedral and radians of 4 points. There are lots of functions of this nature. So if you find yourself thinking that you want some sort of numeric function, it's probably already been written and you shouldn't implement it yourself. Or look first before you implement it yourself. Okay, so let's move on to core. So in core 1, we have graph, which I've told you about already, and then types.hh. There's not a whole lot to types.hh, but everything depends on it because everything uses this size type def and this real type def. Size depends on the amount of memory that your system has available to it. Rather, if you have a 32-bit operating system, then your pointers take 32 bits. And so you'll point to an address in memory with 32 bits. And so size will be a 32-bit integer, unsigned integer. If you're on a 64-bit operating system, then size will be 64 bits. So size is exactly the size as the pointer of a pointer on your system. And like I said, they're unsigned, which means that they're not closed under subtraction, and that can lead to lots of funny things. So if you, for instance, if you iterate from 1 to n, but n is computed as 5 minus 6, then that can, instead of taking no time, take forever. So watch out for working with unsigned integers. There's type def to real, which we have as double. This is actually controlled. This nature of this type def is controlled by some macros, so that if you want to, you can build Rosetta so that real is a float instead of a double. So that can reduce the amount of memory that Rosetta is taking. That may be useful in certain circumstances, but that's the reason why we have this type def here and why we use real everywhere as opposed to double. One other one that's kind of useful is this packer energy. I'll talk about this one a little bit more on Friday, but it's basically in the packer, our energy function is low resolution enough anyways, so that we're not going to use double precision for it. And because memory seems to be one of the chief limitations inside the packer, it's better to use a float here than a double. Okay, so yeah, go ahead.
So you recommend we use unsigned? The size is an unsigned. There is an assigned?
there are other type defs in this. So there's an S size, which is a signed size number. Yeah. One of the reasons we use size so much is that we often iterate over the elements of a vector, like a standard vector or utility vector 1, where we say, for I equals 1, I less than or equal to vector name dot size. And if we get warnings of complaining about the comparison between a signed and an unsigned integer, unless we have the type of I being an unsigned integer. So that's why we use size everywhere.
But obviously for numeric work, it doesn't
Yeah,
make sense.
then you'll want to use integers.
Okay, integers or SI.
S size, sure. Yeah. Okay, so in core 2 we have a fair amount of meat here. I'm going to mostly skip over, I think entirely skip over core ID. And one of the main things that I'll talk about is the relationship between core chemical and core conformation. So one of the key architectural decisions that we made was to separate the chemical representation of the structures that we have in Rosetta from the conformational representation of them, which is to say that we have in our chemical layer something like abstract information. We store that in residue type objects. So a residue type will be something like alanine, and it's kind of its idealized platonic form floating off in space. Atom types would be something like a CH2 carbon, where it's not in any particular structure or bound to anything else except that it's probably got 2 attached hydrogens, and the other things that are attached to it are not hydrogens. In our conformation layer, we have actual concrete instances of the classes that of structures that we're looking at. So a residue would be referring to, say, alanine 15 from a particular PDB, like 1 CRM. So it would have coordinates for all of the atoms in that alanine. If you're talking about atoms, then it would be like C beta in alanine, and alanine 15 from 1 CRM would have particular location in space. But each of these has associated with it like the abstract information, and so in the conformation layer has a pointer back to the associated element in the chemical layer. So you can ask a residue, what's the atom type for your C beta, and it will answer, it's a CH3 carbon. So the way we do this is we have we have classes in residue type, classes in core chemical, such as residue type, which has information about sort of abstract descriptions of residues. So each residue would be given by, say, the number of atoms that it has, and then for each atom you would have, say, identified by index, you would be able to access its atom type. And then in parallel, you have class residue, which has a reference to the residue type that it corresponds to. So if this were alanine 15 in 1 CRM, then this would be a reference to the alanine residue type. And then this utility vector 1 of atoms would give you the actual coordinates for each of the atoms. And the size of this vector would be given by this variable here. So it would have n atoms entries in this vector. So this bits of the bit of conformation information, like the coordinates, is kept up. Corresponds to information out of residue type, because these two data structures share a common indexing. So you can ask for atom 5 from a residue, and then get information about the abstract information of it for atom 5 in the residue type. Yeah. So that, because the residue has to know where to go to get its information. Sorry, is that the question?
Yeah, I guess I don't understand the answer.
So if you were to say, I've got residue R1, right? So R1 dot atom type, and then I would give it 5, right? So that would be the query, or the function that I'm calling. So I'm giving it the index atom 5, and then I call it on an instance of class residue. So that function would then go to the type and ask it for the atom type for atom 5. And so to get from one of these guys to one of those guys, you go through this pointer, or through this reference. Okay, so I'm just going to tell you a few other things. So residue type is actually a fairly large data structure, but I'm going to tell you about a few of the the properties that it has to help describe the abstract information about a residue. So I've already told you that it has a set of atoms, and that for each atom you have a set of there's information about those atoms stored in this atom type class. You'd also have arrays giving you indices of some of these atoms. So this would be like a subset of the atoms that all share a certain property. So for instance, this array gives you the acceptor positions. That's the atoms, the indices of the atoms that are acceptors. This is an array giving you the indices of the atoms that are polar hydrogens. So when you're computing hydrogen bonds between two residues, most of your time is spent figuring out that there are no hydrogen bonds between two residues. And so it's faster to iterate just over the set of atoms that could form hydrogen bonds than it is to iterate across all atom pairs. We also have this vector path distance, which represents the chemical separation of every two atoms in a residue. And this is useful when you're calculating the Leonard-Jones energy, because you always have this caveat, it's D12 minus D6, or 1 over D12 minus 1 over D6, except for atom pairs within 3 chemical bonds of each other. So you have to be able to answer very rapidly, are 2 atoms within 3 chemical bonds of each other? And then we also have this sort of lightweight version of it for atoms that are within 4 bonds of each other. So this is computed, Yesterday I was talking about path separation in the graph lecture. We use Warshall's algorithm, which is this order n cubed algorithm to construct this array. So this is a fairly expensive operation, and it has to be, since we would be interested in the result of that computation in inner loops, we want to have that pre-computed and available up front. Okay. So every atom has an associated atom name, and so you can get to the atom name from its index. You can also go back from the atom name. If you have the index, you can get the atom name. And if you have the atom name, you can get the index using a standard map. So this would help you map back and forth between names and atoms. So if you want to get C beta, you can ask for the index of the C beta atom. Excuse me. And then one of the other things that a residue type stores is the set of residue connections that it is able to form with other residues. And that'd be, for example, you would have, for alanine that appears in the center of a protein, you would have 2 residue connections, one at the N atom and one at the C atom, that would allow it to connect in either direction. Cysteine also has 2 inter-residue connections, one at N and one at C, right? But cysteine can form disulfide bonds, right? So what about the third one? It's actually represented as a separate atom type, or a separate residue type. So we have this other one called CID, which is this disulfided cysteine, and that one has 3 inter-residue connections, and the third one is at SG. The residue connection information holds idealized information about the inter-residue connection. So what's the expected bond distance between the connecting atom and the other atom that it's going to be chemically bonded to, and what's the expected angle. And that's useful for figuring out the chemical connectivity of the conformation that you give to the residue type at construction. Other useful things to know, a residue type has a name, and that name uniquely identifies that residue type in the context of a single residue type set. So in FA standard is the most common residue type set that people work with. There are other residue type sets, including the centroid residue type set. So there's an ALA for alanine in FA standard, and there's an ALA for alanine in the centroid mode. So ALA is unique within FA standard, but not, say, unique within the entirety of the program. Each residue type also has this access pointer up to its owning class. So you can ask, so if you have a residue, then you can ask for its residue type. If you have a residue type, you can ask for the residue type set that contains it. So you can query, given a residue, whether it's an FA standard residue or a centroid residue, by asking for the residue type set. And residue type set similarly has this map from names of residues to pointers to those residues. So there would be an entry in here, ALA for alanine, that would point to the alanine instance of this residue type. Let me talk briefly about the topology file that we use to describe our residue types. It's a text file, and there are lots of these within the Rosetta database. This is the example for the serine residue type that you'll find very many directories deep in a ser.params file, if you were to look for it later. In this, you give the name of the residue. You talk about how you would identify it, describing it either as to the PDB file. So you have to give a 3-letter name for the 3-column residue type, or a 1-letter name for a FASTA formatted file. You can say that this is a polymer residue type. You can identify the amino acid for this, which is serine. The amino acid enum that I haven't mentioned so far is used by our knowledge-based potentials. And so for certain residue types that you might consider adding, we wouldn't have, say, enough knowledge of those residue types to include as part of our residue types. For our knowledge-based potential. So you would say AA unknown or UNK at this position. If you were, say, adding carbohydrates or some strangely modified unnatural amino acid or something like that. And then once you've given some preliminary information, you can list all the atoms. You give the name, and this is a sort of a column formatted thing so that you can identify it from the PDB. So there are 4 columns for the name, so it'd be like space, N, space, space. Then you give the atom type name, so this is the backbone nitrogens, or NBB. Here's the atom type according to charm, and then the partial charge for that atom. This residue type lists 2 residue connections. Since it's a polymer, it has a lower connect and an upper connect, and those are at atoms N and C. And then once you've listed this information, you can talk about the bonds within the residue type. So you say N is bonded to C alpha, and N is bonded to H. And there's a long list of these, longer depending on the topology of your residue type. You can list then the chi angles that describe the side chain. So these are the 4 atoms that define chi1, N, C alpha, C beta, and O gamma. And these are the 4 angles the 4 atoms that define chi2, C alpha, C beta, O gamma, and H gamma. Since this last chi defines an angle that gives the position of a proton, we have the special information for proton chi angles. So you say that chi2 is a proton chi, and then if you wanted to define how, the parameter file has to define how it's sampled. So you say that there are 3 samples at 60, negative 60, and 180. And there are extra samples that are, there's 1 extra sample, and it's at 20 degrees plus or minus each of those 3 canonical places. There are additional properties that you can give it. For instance, this one is polar, and its side chain has orbitals. If you're working with Stephen Combs' orbital code, it needs to have this information. You define a neighbor atom, which is used to figure out whether 2 residues are within striking distance of each other, such that they would have an interaction energy. And then you need to have a radius that says, that's computed so that under all dihedral angle assignments to this residue type, no heavy atom is further than this distance away from your neighbor atom. And then you also have to identify which one is the first side chain atom. In this case, it's C beta. And then for our polar coordinates, for our FA pair potential, we have to identify the action coordinates. So that's encoded here, which is just at, in this case, O gamma.
An example of the sort of bad behavior that the NBR radius is used to avoid?
So the purpose of the neighbor radius is to quickly determine whether two residues have some interaction energy or not. You would use just the C beta atoms to figure out whether two residues are within a certain distance of each other. So it's faster to compute, just a C beta distance than it is to compute all atom pair distances.
Which one is the one that constrains torsion angles?
Oh, so you're talking about the neighbor radius, right? But you said constrains torsion angles? Sure. Okay. Yeah. So you don't know where all the rest of the atoms are, but you're going to try to represent your side chain or your whole residue as a sphere. So let me give you an example here. The markers are gone.
So it's not that that's to avoid bad conformation, but it's to put like an upper limit on the distance.
Yes. So if you say that this is the center of a sphere, C beta is the center of a sphere, and then you guarantee that all other atoms are within 3.4473 angstroms of that C beta, then you can figure out quickly that two residues are too far apart to have any interaction energy. So this is actually very useful for scoring a structure. So you have some interaction distance given by the score function, you have some size of your residues, and then you're just going to compute the distance based, or the C beta distance between those residues, and then figure out whether they have any interaction energy.
The neighbor radius is representing the amino acid as a sphere.
Yes. Yeah. And then this is the center. The C beta is going to take the coordinate of the center. Yeah, exactly. Could somebody look for the markers when they get a chance? Okay, so the residue type parameter files, just as the last thing that's in here, you specify the internal degrees of freedom for each of the atoms. I'm going to highlight two of those atoms. Thanks, Sam. So the first would say the O gamma. You give it 3 floating point numbers and then 3 other atoms. So in this case, O gamma's parent is C beta, its grandparent is C alpha, and its great grandparent is N. And to compute the coordinate of O gamma, you use these three parameters, which are the torsion angle from the great grandparent, grandparent, parent to child, which is this first column. You have a improper bond angle, which is 180 minus the angle between the grandparent, the parent, and the child. Oops, switch lines. So in this case, 67 degrees is like the opposite of, I guess you'd say 180 minus 67 or 68 degrees is 112, right? So that would be the bond angle. Forgive my math if it's not quite right. And then you have a distance between the parent and the child, which is 1.4 angstroms. So that's how you would describe the internal degrees of freedom for, that's how you would construct the coordinate for O gamma from the coordinates of its ancestors. So there's sort of a tree description of how you get to each atom. There's some interesting cases here where, for instance, the coordinate of C beta is governed by, I'm going to get this wrong, but I think it's phi, right? So as you're swinging phi around, it swings C, but coming with it is also C beta. So C beta's coordinate is given as an improper dihedral angle off of, so there's the child, C beta, the parent is C alpha, the grandparent is N, and then the great-grandparent is C, but this is the C not from the previous residue, but from itself, from its own residue. So you have phi giving the coordinate of C, but then you use an improper bond dihedral here to give you the C beta coordinate. So that's what's going on there. Yeah?
So you always use improper bond angle. Is there a reason?
Here, if you have a coordinate frame, say pointing so that the axis, say the z-axis, is along the axis from the, so the coordinate frame is sitting at the parent, and the bond axis is from the grandparent to the parent. So this is at C beta, and here's C alpha, and this axis is pointed up like that. In order to get to O gamma, you perform a rotation by along negative x of this angle. So it'd be a negative x rotation of 67.9 degrees. And that gives you the internal angle here is now 112, but the exterior is 67.9 or whatever. Yeah. So it's, yeah. You could easily have the code compute 67.9 by just giving the internal bond angle and then subtracting. But that's not how it's set up. That might be nice. Okay. All right, so let's go on to, how am I doing on time out of curiosity?
9:20.
We started at 8:30. Okay, so I think we're doing okay. All right, so class residue, like I said, it has a pointer to class residue type, and it has a vector of atoms. Atom itself has a coordinate, and then it's got two pieces of useful cache data that goes along with it. The Rosetta atom type, which is just named as type, represented as a 16-bit integer here, and then which is known as a short, and then the atom type, or the charm atom type, also given by a 16-bit integer. So let me show you just a couple other things that's inside class residue. You have its sequence position, so each residue knows where it is in the pose that contains it, or the conformation that contains it. It has a set of connection IDs in this connect map variable that stores how this residue connects to other residues in the containing pose. So for instance, alanine connection number 2 on this residue, if this is residue 10, that might say that it connects to residue 11 at its connection number 1, which is a very verbose way of saying that alanine 10 has a C to N connection to the previous residue, or to the next residue, right? So it's kind of verbose, but it means that this gives it a way so that you can replace residue 11 without having to update residue 10, so long as residue 11 has certain properties, like the new residue 11 has certain properties in common with the previous residue 11, which is simply that the residue have analogous residue connections. So it doesn't have to have the same number of atoms. It doesn't have to have an indexing that's consistent between them. It just needs to have the same meaning to its connections. And I'm not aware of yet anyone who's had trouble dealing with inter-residue connections the way this is set up. But if you hit them, please talk to me about it. Okay, so I think that's all I was going to say about class residue. Conformation consists of a number of different things. One thing it consists of is a vector of residue owning pointers. And the main way that you get access to a residue is by asking for it from the conformation's residue function. So you give it the index. So if you wanted residue 10, you would say residue and then in brackets, or in parentheses 10, right? And it gives you, and this is a const function, it gives you a const reference to residue. And what's kind of crucial about the way that conformation handles its data is that it does not give out non-const access to any of its residues. This is so that it can maintain, that's the wrong direction. Oh, no, it's not the wrong direction. I've just forgotten what I was going to say. Yeah, no, these slides are out of order. That's what's going on here. Okay, so I'm just going to skip this slide. There's other things that's in class residue. I'll let you read it later. Okay, so the reason that that conformation does this is that it needs to maintain consistency between its residues and then the information that's held in the atom tree. So Matt mentioned before that the conformation holds a fold tree and an atom tree for managing the kinematics of the system. So the residues, they have an XYZ coordinate for each atom, and the atom tree has an XYZ coordinate for each atom. And this data needs to be kept in sync. And so if the conformation let you have non-const access to its residues, then it couldn't guarantee that you weren't changing those coordinates. And then it would lose the ability to ensure that residues and atom tree were up to date with each other. Instead, by gating how you have access to it, it enforces this data integrity requirement that you never be able to access out-of-date residues or an out-of-date atom tree. Okay, so you can set its coordinates. Residue lets you set its coordinates, but conformation doesn't want you to do it, at least not from the residue. So you can tell conformation set XYZ for a coordinate, but then it knows that you did it. But if it just gave you a non-const access to a residue, you could set the XYZ for that residue without conformation being aware. So when you call conformation.setXYZ, it's writing down that you just called that function. And this allows us to have this lazy coordinate update algorithm where what you do is you say set doff, set doff, set doff, like say for all the doffs in the pose, and it doesn't go and recompute the Euclidean coordinates each time. It waits until the first time you ask for the coordinates. Like if you ask for a residue, it says, okay, well, are the coordinates now out of date with the internal like Euclidean coordinates out of date with the internal coordinates of the system? If so, then recompute all the Euclidean coordinates and then store them in the residue objects. And this is lazy, which has two advantages. It's fast and it's always right. So you can never get coordinates that are out of date, and that's really handy. In previous versions, you could say to set XYZ and set doff, and then you start reading coordinates, and who knows if they're right or not. So you always have to say refold, which would refold the entire structure from beginning to end. And so you probably called refold more often than you actually needed to, and sometimes you probably read information that wasn't up to date. And then you're not computing what you expect to be computing. In order to in order to allow this to be lazy, this function will actually call refold, right? So you're calling a const function, and you're going to change the coordinates of these residues. In order to do that, it has to be able to modify this data inside a constant function. And so for that reason, residues is a mutable data member. So this is sort of the extra level on const correctness from yesterday, which is that const may be from the programmer's perspective. I'm sorry, from the user programmer's perspective, as opposed to the class programmer's perspective. So the class may say, I'm going to change my bits. I'm going to flip ones and zeros as is necessary inside a const function, but I'm not going to let you make certain kinds of modifications in a const function. So you can't call set XYZ if you have a const conformation, but you can ask for a residue if you have a const conformation. And in that, the residue may have to the conformation may have to update its internal data in this lazy fashion. So here are these functions: the set doff, set torsion, set XYZ. Like I said, the conformation is going to keep track. Every time that you call this function, it's going to record what kinds of modifications you made to the structure so that it can efficiently update the internal data that it has, the consistency between residues and the atom tree. It also is the way in which we model symmetry in Rosetta is through these functions. So instead of changing residues directly, we actually have a set of we declare these to be virtual functions here. And then there's a derived conformation class, which is actually going to override these functions with its own implementation of them. So the symmetric conformation has the same set of functions. It has set doff, set torsion, set XYZ. And what happens is, say you're working with a trimer. You've got your A subunit, your B subunit, and your C subunit. And let's say you're looking at residue I on the A subunit. And then its symmetric clone I prime is on the B subunit. If you set, say, a torsion for chi let's say you give a torsion ID for one of the chi angles on residue I, and you set that torsion to something. Then the symmetric conformation sets it for this residue, but it also sets it for I prime. So it makes sure that there's a consistency between the internal degrees of freedom for the A subunit, the B subunit, and the C subunit. And that's how symmetry is implemented in Rosetta. These subunits are still present. They're not implicitly represented. They're explicitly represented, but you only have the power to change the asymmetric unit. And this information is managed in the sim-info object. The symmetry info object describes the state of the system, the setup of the system. So kinematically, the way this works is that you have some residues here. So like BB clones would say for residue I that I prime and I double prime are clones of that backbone position. And then you also have jump clones. So the topology is that you have this root of your fold tree, and then there's a jump to some virtual residue, and then there's another jump to the first residue in subunit A. And that's mirrored by a pair of jumps to to the subunit B, and a pair of jumps to subunit C. And then you would say that this jump is a clone of that jump, and this jump is a clone of that jump. So these are the jumps in the asymmetric unit, and these are just clones of that. And so it enforces, the symmetry info helps the symmetric conformation class enforce perfect symmetry of the system. Okay, so core 3, okay, at time? 9:32. 9:32. And this is going to go to 9:45? Sweet. Okay, so I'm going to talk a little about, mention briefly what Pose is. You've already had some experience with this. Talk about the score function and the way we represent the energy method hierarchy. All right, so core Pose is a lot of things, but it's mostly a conformation and an energies object. And it manages the shuttling of data between conformation and energies to make scoring efficient. So every time the conformation updates itself, it keeps track of what has changed since the last time it was scored. And then when you score, the Pose is responsible for getting that information to the energies object so that the energies object can efficiently update itself in the middle of scoring, or at the beginning of scoring. There's also a constraint set, which is part of Pose. Constraints are a really useful way of incorporating external data into your system, or portions of the score function that we don't explicitly model that maybe you're interested in. And Tim will talk about those on Friday. In core scoring, we have this score type enumeration, which starts at 1 for the FA attractive term and goes on to 2 for FA rep and 3 for FA sol, and it goes down a very long list. And it ends with the n score types entry in this enumeration. And then corresponding to n score types is this class energy map, which is an array of size n score types. So this is known at compile time. So this array gets allocated on the stack. So it's pretty quick to allocate and deallocate an energy map. But there are a lot of entries in this. And then the energy map is used in a lot of places, but also in class energies. As I said, it's one of the 2 main data members of class Pose. So for each residue, it has a collection of its one-body energies. So the internal degrees, or the internal energies, so the intra-residue attractive and repulsive term, the Dunbrack energy that looks at the dihedral angles. These would be stored as one-body energies, and then it stores 2-body energies in what's known as the energy graph. And we talked about that just a little bit yesterday. So the edges on the energy graph are going to hold residue pair energies that have just been computed. So the energy graph is kind of fun. I can go into some details here, but one previous implementation for this was to have each edge in the energy graph hold an energy map. But because the score type enumeration has now like 250 entries, and there's only like 12 ever active at one time, the energy graph was taking a considerable amount of memory in representing a lot of zeros for inactive terms. And so a slightly more efficient representation here is to use this array pool element class, which is a small array. It's allocated on the heap, but it's allocated in blocks, large blocks of, say, 32 or 256 of these small arrays at a time. And it's managed by this array pool class. And then all the arrays in this pool are exactly the same size. So if there are only, say, 6 two-body terms that are active in the score function at one time, then each array element will only have 6 entries in it. And so this makes it a much lighter weight implementation of this. And it's managed by this. So when you ask for an entry, say, for FA attractive, there's one array for the entire energy graph, which will map from the FA attractive enumeration value to which index it is in this array. So if you look at how the energy edge will give you the value for a particular score type, what it does is it figures out what the index is, this score type to active, what is the index here, AID. And so if AID is greater than 0, then you look into this small array at that position. If it's equal to 0, then you return 0. It's as if, because that score term is not active, you would say that its value is 0. Cool. So, yeah, go ahead.
I'm still confused about the differences between the energy graph and the energy map. I've heard both terms. I don't know.
The map is an array.
Okay.
Yeah. So it's just an array. It's a long array. And the graph is a decidedly more complicated data structure for representing, nodes and edges, and so you can go to an edge or a node in the energy graph and iterate across all the energy edges for that node.
And this is the residue that you have?
Yeah, and they're stored on the edges in the graph.
Okay, where's the energy map? Is this?
It's an array
Oh.
it's an array of floats, right? And you can do a lot of different things with it. One thing is you can store an array, so it would have one entry per term. So if you wanted to know what the FA sol energy for a pair of residues, you could store an energy map for each pair of residues that was interacting.
Okay.
Energy map is not a map; it's an array.
Yeah.
So that's kind of a funny name for it, but you can only. I mean, so.
I don't see why we need both like that.
Well, they serve very different purposes.
Okay.
The energy graph, you would have, say, one edge for every interacting residue pair. So you'd have, like, I don't know, if the average number of neighbors is 40, if you have 100 residue pose, then you'd have like 2,000 edges in this graph. In the energy map, so each edge would want to hold a different value for each term that was on. So you could hold 0.5 for the attractive, and or negative 0.5 for the attractive component of the energy function, the Leonard-Jones attractive component, and then positive 0.1 or something for the repulsive component for that residue pair, right? So you would have one entry for every active component for just I and J, and then one of those, so an array holding that information for every one of your edges in the whole structure or the whole graph. Whereas the energy map would be that array, where you just have one entry for each of the score types. Great. So, so core 3. I'm sorry. So, the energy method hierarchy is this nice way of abstracting the definition of a new scoring term from its use in the various algorithms that rely on components of the energy function. And so energies are represented with the space class energy method. They're broken down into 3 groups: the one-body energies, the two-body energies, and then the whole structure energies. These would be things that depend only on a single residue, or energy terms that depend only on a single residue, energy terms that depend on 2 residues, and then energy terms that depend on the entire structure or some large subset of the structure that's more than 2 residues. Within this, they break down further into the set of context-dependent and context-independent energy functions. So if you think about the context-dependent terms, that means that the energy for a residue depends on, or for a residue or for a pair of residues, depends on the surrounding residues. And so it's like borderline whole structure energy. But if it's implemented in, say, like a fairly clever way, then it can still be used, say, in the packing algorithms that I'll talk about more on Friday. So, for instance, the strength of a hydrogen bond in Rosetta depends on the number of neighbors for residue I and for residue J. And so if you have a hydrogen bond in the center of the structure, let's say it's like a protein-protein interface, and chain A has a hydrogen bond with itself, and you remove chain B, then chain A gets exposed, and these two residues would have fewer neighbors, and the strength of its hydrogen bond would decrease. So there's sort of an improvement of hydrogen bonding energy that's given by the burial of that hydrogen bond. So that's a context-dependent two-body energy. And then you have context-independent energies, which are just the opposite. It says that if you have I and J floating in space or I and J in some crowded context, their interaction energies, assuming they haven't moved with respect to each other, would be exactly the same. So, so for the one-body energies, you have context-independent one-body energies and context-dependent two-body energies. And then we have a division that I'll talk about in just a moment, but there's a context-independent and dependent form of each of these two. And then whole structure energies are just context-dependent, sort of by nature. And the last division that I'll talk about is the division between short-range two-body energies and long-range two-body energies. And this distinction is a little descriptive in its name. So short-range is definitely descriptive, which is that there's some distance cutoff d for your energy function, such that if all heavy atoms on I are further than d angstroms away from all the heavy atoms on J, then the interaction energy between I and J is guaranteed to be 0. So for the FA attractive term, you can set this from the command line with the FA max dis flag, but it's typically 6 angstroms. So if you have two residues such that all heavy atoms are further than 6 angstroms from each other, then those residues are not interacting according to the Leonard-Jones term. So that means that whether or not, so there's some range, and it's typically a short range that governs whether or not you need to score a pair of residues. And that's used by the score function and other places to figure out what it needs to score. And the opposite of that is just that there is no such cutoff. And we call these long-range two-body energies. But that doesn't necessarily mean that it would apply to all residues at all ranges. It just means that there's no cutoff distance for which you can say they don't interact. So examples of this would be the constraint energy. You can constrain two residues to be 40 angstroms apart. You can say, I know from biological data they're nowhere near each other, so don't give me any simulations where they are. And you could implement this efficiently so that you're not evaluating every interaction at 40 angstroms, but instead you say, for this particular I and this particular J, I want to evaluate their energy regardless of how close or far apart they are together. Right, so short-range two-body energies, they store their interaction energies in the energy graph, and they're not responsible for which residue pairs to evaluate. Instead, that's left to the energy function consumer, like the score function, which will figure out who needs to score. And it's also left to the packer, which figures out which residue pairs it needs to score. Anyone who wants to, say, divide or partition the energy function into small units would be responsible for figuring out which pairs of residues to evaluate a short-range two-body energy between. The long-range two-body energies, on the other hand, have to say who they define energies for. So and the way they do that is by providing this long-range energy container, and they put it into the energies object, and that's what the score function uses then to iterate across the residues that actually apply for that energy function. So for the constraint energies, let's say it was residue 10 and residue 50 that you wanted to make sure were 40 angstroms apart, it would provide a container such that you could iterate across that container, and it would say to the score function, you need to evaluate the energies for residue 10 and 50 together. And that's the purpose of the long-range energy container. The interface for the two-body energies, I'd just like to say this is residue pair energy, and it takes a number of arguments, the pose, the score function, and then the two residues that it depends on. And then it will write down its answer in the energy map object. So it's an array, and it will increment the positions in this array that score term defines for. So for the E-table energy, it defines the FA attractive, the FA rep, and the FA sol terms. And so it would increment into this energy map the total residue pair energy for R1 and R2 into the input energy map. So it comes in as a non-const reference and gets updated inside this call to residue pair energy. So score function is a couple of things. First, it's a weight set. So you would say FA attractive weight should be equal to 0.8, for instance, and that would activate the E-table energy. And it's also a container for the different classes of energy functions. So there were 7 that I talked about earlier: context independent and dependent one-body energies, short-range two-body energies, and long-range energies, and the whole structure energies. And they're held in basically standard lists of pointers to instances of these objects. So just returning to what I described yesterday in rescoring a pose. So this is the process where you would rescore a pose. So you're going to get the domain map out of the pose and drop energies from the energy graph between pairs of residues that have different colors. Then you'll detect the set of neighbors using the point graph that you used in the exercise last night. And then you fill this point graph such that every pair of residues within a certain distance cutoff has an edge in this point graph. It iterates across the point graph and asks if edge I and j connect two residues with different colors, and if those residues are within their cutoff distance, which is dependent on the neighbor radii for I and for j, and for the maximum short-range cutoff. So if the maximum distance is 6 angstroms, and you've got two residues, each with 3 angstrom radii, then if their C betas are within 12 angstroms of each other, then they'll get an edge in this in the energy graph. And if neither of the residues is virtual, then you go ahead and add an edge to the energy graph. All right, so you've done steps 1, 2, and 3. Now you're going to iterate across the energy graph. You'll rescore the context-dependent two-body energies because the context has possibly changed. It's sort of unknowable whether or not the context has changed. And then you'll ask whether this edge connects two residues with different colors. And if so, then you calculate the context-independent two-body energies. Otherwise, you reread the energies that are already stored on that edge because they're still valid from the last time the pose was scored. And if you did rescore, then you store those residue pair energies on that edge for reuse the next time you score. You iterate across all the residues. You rescore the context-dependent one-body energies. And then if the internal degrees of freedom have changed for that residue, then you score the context-independent one-body energies. Otherwise, you can reuse them from the last time they were scored. And then you iterate across the long-range two-body energies, and then you fetch their corresponding long-range energy container, and then iterate across all of the entries in that long-range energy container, and it operates with an interface like that of a graph. So you iterate across all residues I, and then all upper neighbors of residue I, and then score each pair, rescore each pair if it's context dependent or if I and j have moved with respect to each other since the last time you score. And then you evaluate the whole structure energy. And that's sort of a more complete description of the process of rescoring a pose. Right. What's nice about this is that if you add a new scoring term, you figure out where your term fits in the energy method hierarchy, and you don't have to change any of this logic. The score function doesn't change even when we add new terms. And that's really, really handy. It'll make it a lot faster for you to try out new energy terms, and it means that they'll work with a higher degree of certainty than if you were trying to figure out exactly how to update this so that it was aware of your particular term. I think that's it. Any questions? Excellent.